So let's continue our talk about inverses here. This is the second video in the inverse series. We're going to do a couple examples. So in this case, we are given a function, f of x equals 3 times the square root of x plus 4. And we're asked some questions. Is the function 1-to-1? And if it is, we want to find the inverse. We're also going to state the domain and range of the function, and then find the domain and range of the inverse function. So the first thing we want to know is the function 1-to-1? And you can type this in your graphing calculator, but what you're going to notice is that this is the graph of a square root function. That's my parent. The plus 4 means it's shifted left 4 units, and the 3 means it's stretched vertically. So if I shift this left 4 units, we'd be over here at -4 on the x-axis, and stretching it vertically by a factor of 3, that's going to make it 3 times as tall. So the graph looks roughly like this. And if we look at this picture, if I ask you, is this 1-to-1? It's not possible to cross this graph more than once. Any horizontal line I draw would be crossing it only once. So in this situation, yes, this is 1-to-1, which means the inverse will be a function. Okay, so let's talk about the domain and range of this function. So I have my graph. The domain of f is that my x values are going to be from -4 to +infinity. And the range of f is going to be that my y values are from 0 to +infinity. So I know my domain and range. And before I do anything, I can go ahead and find the domain and range of the inverse, because those are going to switch places. So the domain of f inverse will be that my x's are going to be from 0 to infinity, and the range of f inverse will be that my y values are now from -4 to +infinity. So this is the domain and range of my inverse. All right, and when we get to the end and we have our inverse function, let's think about what that means and how that's different from what we would get if I just looked at my inverse function to find my new domain and range instead of switching the original domain and range. So in this situation, I'm going to let y equal 3 square root of x plus 4. So I've replaced f of x with y. Now I need to interchange my x and y value. So this becomes x equals 3 square root of y plus 4. So I'm going to run through my steps to isolate my y, because once I have that new y alone, that is going to be my inverse function. So I need to get the 3, the square root, and the 4 away from that. So in doing this, I'm going to divide on both sides by 3, which gives me x over 3 equals the square root of y plus 4. I'll square both sides. X over 3 squared, and squaring the square root cancels it. So I have x over 3 quantity squared equals y plus 4. And I'll lastly subtract 4. So I've got x over 3 quantity squared minus 4 equals y. And x over 3 quantity squared, that's the same as saying x squared over 9 minus 4 equals y. All right? So my inverse function here, my inverse function, f inverse of x equals 1/9 x squared minus 4. So we replace that y after we've isolated it with f inverse of x. And we know the domain and range of this. So let's talk about this for a second. My inverse function that I've written in the box, that is quadratic, and the shape of quadratic functions is a parabola. That's a quadratic function. We know that it is shrunk vertically by a factor of 1/9 and shifted down 4 units. So if I went to graph my inverse function, I would get a parabola shifted down over here at -4, and it should be smushed vertically, compressed vertically, so it is 1/9 as tall. All right, so it's kind of like, think about squishing a peanut butter and jelly sandwich. It's a little wider than a typical parabola. Now, if I took this and reflect my inverse function across the identity, would I get two functions that match up perfectly? No, I wouldn't, because the domain of this parabola that we're looking at here is all real numbers. Of course, I found my domain by switching the original domain and range, and so in this situation, I only need the right half of this parabola. So we only have this much of it, because we're saying the domain is from 0 to positive infinity. So now if I put my original function, I'll do f of x over here in yellow, we see, okay, we would get something that looks like it would reflect over the identity. So in yellow I have f of x, and in this dark blue I have my inverse function, f inverse x. Okay, and if I had just looked at my inverse function to get the domain and range, I wouldn't get the correct answer. All right, so it's really important that you follow the steps and you find your original domain and range and switch them to get the domain and range I've just circled there. So we found an inverse function and we found the domain and range of the inverse. So let's look at another example here. Is the function 1 to 1? If so, find its inverse and then state the domain and range. So before we do this, let's think about the graph. So we have a rational function here. This rational function has two asymptotes. It has a vertical asymptote at x equals positive 2 and a horizontal asymptote at y equals -3. The x-intercept is going to be at -1/3. That's coming from right there. And my y-intercept is going to be at positive 1/2. All right, so if I were to graph this, and of course you have your calculator, you can do that on your own, I get a rational function that bounds up to these asymptotes and looks something like this. All right, so there's my original function. We're looking at the graph of f of x. The domain of f, let me write that over here. The domain of f is that my x values are from -infinity, we can't equal 2, union 2 to infinity. And the range of f is that my y values can be anything but -3. So, in this situation, the domain of the inverse, the domain of f inverse, is going to be that my x values can't equal -3, and the range of f inverse is going to be that my y values can't equal 2. So without even knowing what my inverse function looks like. I was able to calculate my domain and range because I know what the original or the given function looks like. All right, so I'm going to erase this here and we're going to find our inverse. So when I look at finding my inverse, we have y equals 3x plus 1 over negative x plus 2. Now, we're going to interchange my x and y values. So that's 3y plus 1 over negative y plus 2 is equal to x. So notice I had two x's, and when I interchanged them, I now have two y's. Okay, so we need to isolate y, and this is kind of confusing for students sometimes because it's counterproductive to what we want to do. We're going to end up combining y with an x before we can actually get it alone. So in this situation, we'll cross multiply. X times negative y plus 2 equals 3y plus 1. And I created a proportion. I just put that over an invisible 1. So negative xy plus 2x equals 3y plus 1. So you'll notice I have two terms that have y values. I'm going to get both of those terms on the same side, and then my two terms that don't have y values, I'm going to put them on the other side of the equation. So that leaves me with, I've got my 2x plus 1 on one side. Oh, that would be a minus 1. And then I have 3y plus xy on the other side of the equation. So I added, subtracted, used my additive property of equalities or equations to collect terms. Now that both of my y values are on the same side of the equation, I'm going to factor a GCF. And when I factor that GCF, that will leave me with 2x minus 1 equals, both of my terms have a y, so I'll factor that out. That leaves me with 3 plus x. So I collected my y's to one side so I could factor that y out. At this point, we have one step left, which is to divide. So 2x minus 1 divided by 3 plus x equals y. Or we can state that as the inverse function is 2x minus 1 over x plus 3. And if you look at the domain and range we originally found, I erased it from our screen, but the domain of the inverse, we said that x couldn't equal negative 3. And you'll notice if I try to plug negative 3 in here for x, I'll get 0 in the denominator. Also, we said that y would not be allowed to equal positive 2. And y can't equal positive 2 because we have a horizontal asymptote at y equals 2 over 1. And so just to restate that, my domain of f inverse is that my x values can't equal negative 3, and my range of f inverse is that my y values cannot equal positive 2. As we move ahead in math, we're always learning so we can build for our next class, our next adventure. But there are situations where we may need to prove that two functions are indeed inverses. And the way we can do that is to use composition. And what I mean by that is f inverse of f or f of f inverse. So remember, composition, you're plugging one function into the other for x. And as long as you verify the composition in both directions, f inverse of f and f of f inverse both simplify down and give us x, we can prove that these two functions are indeed inverses. So I'm going to do both of these. F inverse, I'm going to plug into F inverse f of x. And what that would give me would be x cubed minus 5. And into that x, I'm going to plug the cube root of x plus 5. So simplifying this, the cube and the cube root cancel. I have x plus 5 minus 5, which gives me x. And if I go in the other direction, f of f inverse of x, that would be the cube root of some x value plus 5. And that x value I'm plugging in is x cubed minus 5. So simplifying this, I've got the cube root, x cubed minus 5 plus 5 goes away. So the cube root of x cubed simplifies to just x. And so we can say, well, yes, these two given functions are inverses of each other. And just to reiterate our idea that the inverse is a reflection over the identity, let's find the inverse given this graph. So finding the inverse given the graph, each of these points I'm going to invert. I'm going to switch my x and y. So 2, 10 is going to become 10, 2. 0, 2 is going to become 2, 0. And my last point, negative 2, negative 6, is going to become negative 6, negative 2. And I could do this for any number of points on the graph, but as I do that, I'm going to see that the curve takes the shape of this. And what we notice here is that these two curves would fold nicely on the identity y equals x and create this perfect reflection. So this is another way we can check that things are inverses. So when you've done the problem, check them, plug both your function and your inverse that you've found into your y1 and y2 on your calculator, and look at the graph. Do keep in mind that your graph, the window, that standard window on your TI calculator, is not a square window. The standard window is a little bit skewed, so you can always choose the option zoom 5, which will make that a square fit. So zoom 6 is standard, zoom 5 will square it, and you'll be able to see that reflection a little bit better.